So welcome back. I'm going to talk in this video about our perception of sounds, starting from this biological picture that I described last time. So let me review that. And so the idea was that when you have a sound wave coming along, in this example, it's a musical tone, so a periodic sound wave. And that means that the displacement versus time of the sound wave coming into our ear is described by some periodic graph like this. That sound wave creates pressure variations near our eardrum, and then the eardrum vibrates basically in the same way with the same displacement versus time graph as the original sound wave. Now, when that goes into our ear, the vibrations of the eardrum cause vibrations of the ossicles, these little bones in the ear. They cause vibrations of this oval window, which leads into the cochlea. So then you have this cochlea that was a rolled up snail-shaped object in your inner ear. But if you unroll it in our diagram, then the structure is that you have a top chamber filled with fluid that connects to a bottom chamber, and in between is something like a membrane, and part of that is called the basilar membrane. So various pure tones coming into the cochlea will excite or cause to vibrate certain specific regions of the basilar membrane. And when those regions vibrate, you end up getting the nearby nerve fibers sending electrical signals towards the brain. So our cochlea is essentially a spectrum analyzer in that it takes in some general sound wave, some time graph describing the vibration of the eardrum versus time, and then the output would be a bunch of nerve signals, and you have specific nerves that tend to get excited by specific frequencies. Okay, so it's not quite this precise. If I send in a 400 hertz frequency, there's actually some range of locations on this basilar membrane that get excited, and so there'll be several nerves that send signals, but it's a pretty good picture to keep in mind. And there's even information about the amplitude of the various components of the sound that are present. So if I have that musical tone, I have all of the various harmonics with different amplitudes, and this amplitude information is also sent to our brain via, it turns out, two ways. One of them is just the rate of firing of these neurons. If you have a larger amplitude, you could have a higher firing rate. So these electrical signals are kind of all the same size, but you can have those going more often. And so the other way is that if you have a larger amplitude, then the region that gets excited expands a little bit. And so you could also have nearby neurons sending their signals. Okay, so the output to our brain you can represent in a graph like this. So like the nerve firing rate versus the location of that nerve along the basilar membrane. And that graph basically contains the same information as a spectrum graph. So let's talk about the physical parameters of sound that we're actually able to detect and process. So we can think about first the frequencies, and then probably in the next video, I'll talk about the amplitudes or the volumes of sound that we're able to hear. So in terms of frequency, then there's a range that we can hear that goes from about 20 hertz all the way up to about 20,000 hertz. And that has to do with physical properties of this membrane. We have, remember last time I talked about how this side close to the oval window is stiff and thinner, and that tends to be excited by higher frequencies. And so right at the end here, that would be where 20,000 hertz frequencies would be able to excite the membrane and excite these nerves. Higher frequencies just are not capable of doing that. And then on the other hand, the lower the frequency you have, the further along this basilar membrane you're going to excite. So this end is longer and floppier and responds to those lower frequencies. But below 20 hertz, again, the sound waves are not able to excite these nerve fibers. Okay, so I'm going to demonstrate this range of frequencies for you, going over to this website that allows me to play a pure tone at various frequencies. And so actually what I recommend right now is just turning your volume down a little bit, and then I'll play the note and just adjust it to a comfortable volume and leave it there. And then I'll scan across the range of frequencies so you can hear. Okay, so starting going down. Okay, so that was going down. Now, a lot of headphones and computer speakers don't really do well playing those very low frequencies. So unless you had a subwoofer hooked up, you probably weren't able, you probably stopped being able to hear that at some frequency significantly above 20 hertz. But so now let's go up from that middle frequency and we'll hear the high end. And so maybe pay attention to at what frequency do you stop being able to hear this. Okay. So for me, that was somewhere, I think it was somewhere between 15,000 and 16,000 hertz that I couldn't hear it anymore at that point. But if you're younger than me, then probably you could hear higher frequencies than that. So one thing to mention is that there are sounds with a significantly broader range of frequencies than this range from 20 to 20,000. For example, if you look at ultrasound scanners, so these medical imaging devices that people use to, well, look at developing fetuses or to look at organs in your body, they're using sound waves, but their frequencies are way up higher than 20,000. They're actually in the millions of hertz. And so we can't hear those sounds, but nevertheless they exist. And so you send these sound waves into your body, they bounce off various organs and developing babies and everything, and they are picked up again, and then the computer deciphers the signal and makes an image out of it. Okay, so we can compare our frequency range of hearing to the types of frequencies that typically appear in musical compositions. And so just as one standard for comparison, the usual range of the piano goes from 27.5 hertz for the lowest note on the piano, which is an A, up to 4186 hertz for the highest note on the piano, which is a C. And so that covers quite a bit of the range. Oops. Although you might say, well, there's a huge range missing from the top end of the piano to the top end of what we can hear. But there's something important to understand about how we perceive frequencies compared to the actual numbers of hertz. And that is that if we perceive a certain increase in pitch and then an equal increase in pitch and an equal increase in pitch and an equal increase in pitch, that does not correspond to just adding a certain amount of hertz each time. Okay, in fact, it corresponds to multiplying the frequency by a certain amount. So we've seen an example of this before. If you go from one note up an octave, so So that corresponds to doubling the frequency, whatever note you start on. And so, so every time you go up an octave, you're actually doubling the frequency. And so if you look at the various A's, these are all A's on the piano, you see that each time you go from one A to the next A, then you actually double. So you don't add a certain number of hertz, you actually multiply by 2. Okay, and so from that perspective, this 20,000 hertz, it's not so far above the 4186 hertz. So if you double that, you'd get 8,000, and double it again, you'd get 16,000, which is already above what I can hear. And so these highest frequencies, so there's like another 2 octaves that you could hear on top of what the piano produces. There's actually been a piano produced that has another octave on top of the usual piano. I'll put a link in the description below. And so that only leaves about an octave of sounds that have not been created on a piano. And those sounds are not particularly pleasant. Okay, so that's an important thing to understand in terms of like how an equal increase in pitch as we perceive it corresponds to a change in the frequency, corresponds to multiplying the frequency by some constant amount. And so we might ask, like, why is that? Why don't we perceive just adding a certain number of hertz to correspond to an equal increment of pitch each time? And it probably partly has to do with the way that these frequencies excite the basilar membrane. So it turns out that approximately it's true that when I go just up octaves, so when I multiply the frequency by 2 and 2 and 2 and 2 again, then if you look at the part of the basilar membrane that's excited by these various frequencies, then those regions are roughly equally spaced on the basilar membrane. And so it makes sense that we would perceive those to have roughly the same interval of pitch between them. I'm going to talk in more detail about the specific reason why this doubling of frequency is important and why we see that as a very important interval in music when we get into talking about multiple tones next time and the following time. So we've talked about that one particular interval of an octave as corresponding to multiplying the frequency by a certain standard amount, which is 2. We could also talk about going up a smaller interval. And so on the piano, it turns out that there are 12 notes going up from one A to the next A, if you're including the black keys and the white keys. And so this smaller interval of going up just one note on the piano is also a particular factor that you multiply the frequency by. So what is that factor? Well, it is a number where if you multiply it 12 times in a row, then you get 2. Okay, and so that has to be true because if you go up 12 of these steps, which musically we call semitones, then you get a whole octave. And so what is the number where if you multiply the frequency by that and then multiply it again and again and again 12 times, what is the number that if you do that, you get double the frequency? Well, it's the 1/12th power of 2. Okay, it's just a number. It's about 1.059, and there's some more decimal places. And so going up one semitone in frequency or in pitch, that just corresponds to multiplying your frequency by this standard number. In terms of percents, this is a 5.9% increase in the pitch, in the frequency of your note. Okay, whereas going up a whole octave was a 100% increase. Okay, so just so you have a bit of practice with that concept, maybe just take a minute to try to use the figure above, use the picture that I've drawn, and see if you can figure out what is the frequency of middle C. Okay, so let's talk about that. And what we're going to do is use the fact that middle C, which is the yellow note here, that is 3 steps on the piano above this A, which is exactly 220 hertz. So what we're going to do is say that if you start with 220 hertz and you go up 3 steps, then each step, each semitone that you go up, you have to multiply by 1.059. Okay, so we want to do that 3 times. I'm ignoring the extra decimal places, but if you want to be more precise, you should take the 12th root of 2 on your calculator and then use that number and multiply that 3 times. Okay. If you want to be a little bit quicker than that, you could use the power. So basically we're going to take 220 and then multiply by the 3rd power of 1.059, and that turns out to be somewhere in the around 261 to 262, depending on how many decimal places. If you use the exact thing, 2 to the 1/12, and you take the 3rd power of that, then it's just slightly higher than 262 hertz. Okay, so that is the frequency of your middle C on the piano. And so one can ask, well, given that you have all of these possible frequencies, what is the finest resolution that we have in detecting the frequencies? So we have notes on a piano, there's 88 of them from the bottom to the top, and we have a pretty easy time telling if I go from one note to the next. There's no doubt that I've changed the note, at least for most of us. So it turns out that our ears are significantly more sensitive than that. We can perceive frequency changes that are definitely smaller than one of those semitones. And so it's an interesting question to ask, well, what is the smallest frequency change that our ears can detect? And this smallest frequency change is something that we call the just noticeable difference, for obvious reasons. And so what we can do is just do a little, let's do a little test now on our ears. So I'm going to play a video where I'll play different intervals which are smaller and smaller, starting from about 2/3 of a semitone and going down. And then you can try to see for yourself what is the just noticeable difference. It's starting in particular from a frequency of 400 hertz. So we're going to do a hearing sensitivity check. We're going to check our sensitivity to changes in frequency. I'm going to do several examples. In each case, I'm going to start with 400 hertz and then either go up 4% above that and then back to 400 and then down 4% below, or it could be the other way around. And so I'm going to do that for a 4% change, and then a 2% change, and then a 1% change, then a 0.5% change, and then a 0.25% change. Okay, so see which ones you can recognize and figure out whether we go up first or down first in each case. Okay, so which ones could you hear? Okay, so I think out of those 5 cases, the 3rd one went up and then it went down, and I think all of the rest of them went down and then up. And I could just barely hear that for the last one. So what that means is that for that frequency, my just noticeable difference was, I think it was about, it said 0.25% of the original frequency. And in terms of the semitone interval, which is about 6%, so that corresponds to roughly 4% of a semitone. So this just noticeable difference, it's different for different people. But for everyone, it actually varies quite a bit depending on which frequency you're looking at. So for the very low notes, then this just noticeable difference can be something like half a semitone or even more. So it's much harder to distinguish between frequencies that are closely spaced in the low range, whereas up in the higher range, like the note we heard, or even higher notes, then our perception gets to be more accurate. And I think most people can distinguish intervals, can hear differences, even in the range of like 5% of a semitone. So in musical terms, these fractions of a semitone are sometimes called cents. So half a semitone, people would say 50 cents, or 5% of a semitone would be 5 cents. So sometimes you hear that an instrument might be 20 cents sharp, which means that it's a little bit has a little bit higher frequency, but it's not all the way to the next semitone. It's just 20% of the way to the next semitone. Okay, so one thing we can take away from that is that there are actually many, many more notes that we can distinguish than those notes on the piano. So it's a little bit arbitrary in some sense that we've decided on the semitone as the basic unit of frequency increment. And we'll talk about some of the reasons for that coming up. But it's just good to be aware that there are, in fact, many tones in between the semitones that would be on a piano. And some types of music actually make use of these in-between notes in interesting ways. Okay, so in the next video, we're going to move from talking about frequency to talking about our perception of loudness. And so check that one out.